I'm going to draw two pictures here, and I want to draw similarities and differences between these two pictures. The first one you're going to recognize from Physics 20. The first one is a hill with a car at the top of that hill. Let's say that that car is not powered, so that it has the ability to move only if there's gravity or some other factor that's causing it to move. It'll just roll, and eventually, okay, it'll either speed up because it's going down a hill, or maybe it's going up a hill and it will slow down. But the bottom line is, it's a go-kart. Let's call it a go-kart. Okay, there's no engine in this car. Let's say the height of this hill is 10 meters. And let's say that in this particular case, the initial speed of that car is 0 meters per second. So the go-kart is sitting at the top of the hill. It's ready to go down the hill, but it's not going yet. We maybe want to find the speed of the car at the bottom of the hill. What would we do? How would we solve this question? You guys remember the concept that we used in Physics 20 for this? It's an energy thing, right? Yeah, it's EI equals EF. Now, let's ask ourselves a couple questions here. Do we have potential energy at the top of the hill? Yes, because there's a height. So there would be mgh at the top of the hill, right? Do we have at the top of the hill kinetic energy? No, because it's not moving. At the bottom of the hill, do we have potential energy? No, Colton, because there's no height anymore, right? Do we have kinetic energy at the bottom of the hill, Colton? Yes, because it's moving. So the equation that we would use to describe this situation is mgh equals 1/2 mv squared. You've got a conversion of potential to kinetic energy. Does that make sense? That is 100% review from Physics 20. Now I want to draw another picture on the right-hand side. This time, let's draw two charged parallel plates. Let's make the top plate positive and the bottom plate negative. That's going to cause, by the way, an electric field pointing downwards. Agree? Yes? Away from the positive toward the negative. Let's put a positive charge in between these two plates right up here. Let's give it an initial velocity or initial speed of 0 meters per second. What's going to happen to that positive charge? It's going to accelerate, yes. It's going to accelerate. It's going to speed up. It's going to be pushed away from the positive plate toward the negative plate. It's going to move, experience a force, and therefore move in the direction of the electric field. I'm positive the force is with the field. So it's going to accelerate. We're going to solve this in virtually the same way as we solved this other question in Physics 20. We're going to say EI equals EF. Think about that. Okay, a couple days ago, we said that when a charged particle goes through an electric field perpendicular to that field, it goes in a parabola, just like a soccer ball goes in a parabola when it's kicked off the edge of a building. So a charged particle in an electric field perpendicular to that field, it's projectile motion. It's like gravity, projectile motion. Well, this is like gravity, but conservation of energy. We're going to say EI equals EF. What kind of energy do you think that this charged particle would have at the top, at this top plate here? Potential. But we're not going to make it gravitational potential energy, because this isn't a gravity problem. We're going to make it electric potential. On your data sheet, you're going to see an equation that looks like this. Delta V is equal to delta E over Q. Delta V stands for potential difference. The difference in energy per coulomb of charge equals the change in energy divided by Q. You're going to find that under the electricity section on your data sheet. Now, we're going to modify that just a little bit. We're going to say V is equal to E over Q. The first one is potential difference. The second one is just potential. The potential, the energy per coulomb of charge at one spot is V, and it's equal to E over Q. I'm going to rearrange that, and I'm going to get Q times V for energy. So the energy, the electric potential energy at one spot is equal to the charge times the electric potential at that one spot. Now, instead of saying mgh for the initial energy, I'm going to say Q times V for the potential energy. Equals, well, what kind of energy does this charged particle have when it reaches the other plate? Kinetic energy. It's moving, right? So it's going to be equal to 1/2 mv squared. Let's change it up a little bit. Let's say that now this go-kart is not at rest. Let's say that it's moving at, let's say, 8 meters per second. Or whatever. Does it still have gravitational potential energy at the top of the hill? Yes. Does it still have kinetic at the bottom? Yes. Is there anything else now? It has kinetic at the top. So on the left-hand side, we'd say mgh initial plus 1/2 mv initial squared equals 1/2 mv squared on the right-hand side. Now, what if I gave this charged particle an initial speed over here? Instead of being 0 meters per second, let's make it, I don't know, 10 to the 4 meters per second. How does that change things over here in problem number 2? It gives it an initial kinetic and potential energy. So instead of just being QV initial, it's QV initial plus 1/2 MV initial squared. What if, in problem number 1 over here, I didn't want to find the speed when it was at the bottom of the hill? What if I wanted to find the speed when it was halfway down the hill? What if I wanted to find the speed right there? Would the first side change, mgh plus 1/2 mv squared? The initial energy would still be the same, wouldn't it? What would the final energy be now? Would there still be kinetic energy halfway down the hill? Yes, not as much though, right? Would there be potential energy halfway down the hill? Yes, because there's still a height. What if I wanted to find the speed of this particle halfway across? Halfway between the top plate and the bottom plate. Still potential and kinetic at the beginning? Yes. I still have kinetic when you're partway across? Yes. Anything else? Potential. Except it's not gravitational potential, it's electric potential. Here's the way I want you to think of this. Whenever you see a charged particle that speeds up, or for that matter slows down, but we'll deal with that in more detail in a few minutes here. Whenever you see a charged particle that accelerates in an electric field, like we have here, I want you to picture it as a car going up or down a hill. Why? Well, because we know how to solve those problems, and we can visualize a car going up or down a hill. Can you visualize this? Can you see this right now? Not this one on the right-hand side. Okay, I have trouble seeing in my mind an electron or a proton accelerating through an electric field, but I don't have any problem visualizing a car going down a hill. Leah, can you see the car going down a hill? Yes? What color is the car, Leah? Black? I don't know. She might have been making that up. She said she could see it going down the hill, but then she paused. Maybe it's kind of getting dark, and maybe it's kind of navy black, and she wasn't sure about that. Is that the case? Okay, how many people are in the car, Leah? Who's in there? Are you in the car? Are you driving the car, Leah? Yes, you do. You're visualizing the car. You can see it. Can you see it? Are you driving it? Yes. Yes, okay. Leah can visualize this car going down the hill, and she can answer every single time what type of energy we have at the top, the bottom, the middle, whatever. It's a little bit harder to do that with a proton or an electron going across parallel plates. It's harder to visualize that. We can't visualize, exactly what it looks like and so on. But if we picture it as the car going down the hill, then we can identify what type of energy we have, and then just, hey, wherever we had mgh, just replace it with QV. Right? Otherwise, exactly the same. Does that make sense? Let's just summarize the types of energy that we gain or lose here, and then we'll do an example problem here, okay? What type of energy in both cases do we lose as, we'll say, as the car goes down the hill? We lose potential energy. So in this case, we lose gravitational potential energy. In this case, we lose electric potential energy. What kind do we gain? Kinetic in both cases, right? Here we gain kinetic energy because it speeds up. Here we gain kinetic energy because it speeds up. What doesn't change? The overall, the total. energy doesn't change. Potential decreases while kinetic increases. Well, the total will always remain the same. And the same deal over here on the right-hand side. Although potential decreases, kinetic increases, giving us a total energy at every point that remains the same. Example number 1. Second to last example of the unit here. It says an electron is released at a speed of 1 times 10 to the 5 meters per second at a negatively charged plate and accelerates toward a positively charged plate. There's a potential difference of 20 volts between the plates, and the plates are 30 centimeters apart. How fast is the electron moving when it's traveled halfway across the gap? Let's draw a picture here, okay? Here is a negatively charged plate. Here's a positively charged plate. That causes the electric field to go upwards from positive to negative. We release an electron right here with an initial speed of 1 times 10 to the 5 meters per second. That electron is moving against the field. What's going to happen to it? Speed up or slow down? It's going to speed up. Right? It experiences, the field is upward. The force on a negative particle is downward. It's moving downward. There's a force downward. It's going to speed up. Car is moving down the hill. The gravity is down the hill. What happens to the car? It speeds up. Make sense? All right. Let's picture this as the car going down the hill. Let's say EI equals EF for the car going down the hill. This car that is moving at the top of the hill has what kind of energy? Potential and kinetic. We're going to say mgh plus 1f mv squared, right? Well, let's replace mgh with qv, electric potential energy. What kind of energy does the car have at the bottom of the hill? Sorry? Kinetic energy, right? So this charged particle has kinetic energy at the bottom of the hill as well, or when it reaches the other plate as well. Let's sub in some numbers here. 1.6 times 10 to the minus 19. It's an electron, but we always drop the sign of the charge. VI is, wait. We're not going to the bottom of the hill, are we? Where are we going? Halfway down the hill. From the top, halfway down the hill. So we're looking for how fast it's moving right here. There's also potential energy halfway down the hill, right? But it's not potential energy mgh, it's potential energy Q times V. All right, VI is 20 volts, right? Plus 1/2 of the mass of an electron on our data sheet times VI, 1 times 10 to the 5 squared. Lots of numbers here. Looking for the speed. Looking for the speed with which it reaches halfway down the hill or halfway between the plates. Charge, once again, is 1.6. Here's one. What's the final potential? What's the final potential? The initial potential was 20. The final potential is, anyone? 10. It's like if the hill was 20 meters high and you've gone halfway down the hill, the final height is 10. Potential difference, potential is analogous to height. Okay? If you're halfway across the gap, your potential is half of what it was when you started. Okay, lots of numbers here. And my calculator, the app that I have for the calculator is busted. It's not working, so we can't show you how to go through this. But know that you would multiply those, multiply these, and then add them together. Multiply these two numbers and take them to the other side by subtracting. Then multiply the whole thing by 1/2. Divide by 9.11, and then square root. Yeah, when you do that, you should end up getting 1.9 times 10 to the 6 meters per second. Does that seem reasonable? Well, we started at 1.0 times 10 to the 5. We're going faster. That's what happens when a car goes down a hill, right? It speeds up. What about when it reaches the other plate, the negative plate? Well, now we've got to the bottom of the hill. So now we're going to say EI equals EF. We're going to say potential energy. Car has potential energy at the top. It has kinetic energy at the top as well because it's moving. But when it reaches the bottom of the hill, it has only what? Kinetic. It is only kinetic. 1.6 times 10 to the minus 19 again. Times VI is 20 times 9.11. The initial speed so get this number, add them together, multiply by 2, divide by 9.11, and then square root. What would you expect to get here? Smaller or bigger than 1.9 times 10 to the 6? When Leah's car was halfway down the hill, it was moving at a certain speed. When it went all the way to the bottom of the hill, it was moving faster. We should get a number that's faster, and sure enough, we do. The answer is 2.7 times 10 to the 6 meters per second. I'd like you to take a look right now, just for the next few minutes, maybe the next 5 minutes, at worksheet number 9. Specifically on worksheet number 9, I want you to do questions 4 and 5. For now, on worksheet number 9. Example question number 2 now says an electron is released in an electric field. It's moving at this speed in the direction of the field. Determine the potential difference required to stop the electron. Okay, this is kind of a hard one to wrap our minds around, I think. Okay, it's moving at this speed in the direction of the electric field. What's the potential difference required to stop the electron? Let's draw this out, okay? Here's an electric field. Doesn't matter which way we have it drawn. Let's say it's drawn to the right, okay? There's the electric field. We have an electron that's moving this way at an initial speed of 5.00 times 10 to the 6 meters per second. Which way is the force on this electron going to be? The field is to the right. The electric force will be to the left. A negative particle experiences a force opposite to the electric field. So if it's moving to the right, but there's a force to the left, what's going to happen to that particle? It's going to what? It's going to slow down. Well, that's like a car doing what? Well, braking, yeah, or going up a hill. What kind of energy does the car have at the bottom of the hill before it begins to go up the hill and slow down? Picture it. What kind of energy does the car have at the bottom of the hill? It's moving, and then it's starting to go up the hill, but of course it's slowing down as it goes up the hill, right? What kind does it have at the bottom of the hill? Kinetic energy. What kind of energy does this electron have before it starts slowing down? Kinetic energy. So now let's say that this car goes up the hill and stops. So it reaches its peak height on the hill and stops. What kind of energy does it have once it's stopped? Potential energy. Well, we're going to say not MGH potential energy here. We're going to say QV potential here, right? So instead of having a conversion of potential to kinetic, this time we have a conversion of kinetic to potential. The total energy will still remain the same. 1/2 mv squared equals QV. Let's say 1/2 of 9.11 times the initial speed, 5 times 10 to the 6 squared, equals the charge, drop the sign of the charge, because we always do when we sub it into an equation, times VF. We solve for VF there. And by the way, that's big V, right? Electric potential, not speed. We solve for that potential. It works out to be 71.2 volts. Now, just a small thing here. It's not really a big deal at all. But I have technically solved for VF, the final potential. What was I technically looking for? The potential difference. I found final potential versus potential difference. Okay, what was the initial potential? 0. Okay, if the initial was 0 and the final is 71, then what's the potential difference? 71, right? Even though technically I found the final potential, it's the same thing as the potential difference, right? Do you understand the difference there? Potentially? All right. I'm going to ask you to finish up questions number 4 and 5 on the worksheet that I signed a few minutes ago, but also take a look at questions 6 and 7 for homework. So total for homework, you've got worksheet number 9, questions number 4 to 7, please.